An existing switchboard has a 1200 amps bus duct rising up the floors of an office building. At the 6th floor, it transitions up to the top with 600 amps. This electrical design modification aims to modify the existing switchboard to handle a reduced load at high floors. The design changes involve several key aspects. Firstly, the existing 1200 amps bus duct from the main switchboard is maintained up to the 6th floor. Secondly, at the 6th floor, a bus duct transition is installed, reducing the capacity from 1200 amps to 600 amps. Thirdly, a 600 amp bus duct is connected to the existing bus duct from the main switchboard. Finally, a 600 amps bus duct continues to power the upper floors, specifically the 7th floor and above. The rationale for this modification is as follows. The 1200 amps bus duct is only required to handle the higher load at the lower floors. By transitioning to a 600 amps bus duct at the 6th floor, the system can accommodate the reduced load at the upper floors while maintaining sufficient capacity. This modification optimizes the electrical system design and ensures efficient and safe power distribution throughout the building. There are additional considerations to keep in mind. Firstly, ensure that the 600 amps bus duct has adequate ampacity to handle the maximum load on the upper floors. Secondly, verify the bus duct connections are properly made and taught to manufacturer specifications. Thirdly, provide appropriate documentation and labeling to clearly indicate the bus duct capacity at each floor. Let's delve deeper into each of these aspects, starting with the 1200 amps bus duct. The 1200 amps bus duct's primary function is to carry the electrical load from the main switchboard to the lower floors where the power demand is higher. This higher demand could be due to a greater concentration of electrical equipment, machinery, or lighting in these lower levels. The bus duct itself is typically constructed of aluminum or copper conductors enclosed in a protective housing. The choice of conductor material depends on factors such as cost, conductivity, and weight. Copper offers better conductivity but is heavier and more expensive than aluminum. The housing provides physical protection to the conductors and also serves as a grounding path. Bus ducts are available in various configurations, including feeder bus, plug-in bus, and low-impedance bus. Feeder bus ducts are used for long runs and have limited tap-off point. Plug-in bus ducts have regularly spaced openings for connecting electrical equipment. Low-impedance bus ducts are designed to minimize voltage drop and are used in applications where voltage regulation is critical. The selection of the appropriate bus duct type depends on the specific requirements of the application. Now let's move to the transition at the 6th floor. The transition from 1200 amps to 600 amps is a critical point in the system and requires careful design and installation. The transition involves physically reducing the size of the bus duct while maintaining a reliable electrical connection. This can be achieved using a transition piece specifically designed for this purpose. The transition piece typically consists of a tapered section that gradually reduces the cross-sectional area of the bus duct. The conductors within the transition piece must be sized to handle the 600 amps load without overheating. The transition piece should also be mechanically robust to withstand the stresses associated with thermal expansion and contraction. Proper ventilation is also essential to prevent overheating at the transition point. The connection between the 1200 amps bus duct and the 600 amps bus duct must be made in accordance with manufacturer's specifications and industry standards. The connection should be tight and secure to minimize resistance and prevent arcing. All hardware, including bolts, nuts, and washers, should be made of compatible materials to prevent corrosion. A conductive joint compound should be applied to the contact surfaces to improve conductivity and prevent oxidation. After the connection is made, it should be thoroughly inspected to ensure that it is properly installed. Now, considering the 600 amps bus duct serving the upper floors, the 600 amps bus duct is sized to handle the reduced load on the upper floors. This reduced load is due to the lower concentration of electrical equipment in these areas. The 600 amps bus duct should be selected based on the maximum load demand on the upper floors, taking into account future growth. The voltage drop in the 600 amps bus duct should also be considered to ensure that the voltage at the equipment is within acceptable limits. The bus duct should be properly supported to prevent sagging and vibration. The support should be spaced in accordance with manufacturer's recommendations and should be securely fastened to the building structure. The bus duct should also be protected from physical damage and environmental factors such as moisture and dust. Now let's discuss the rationale for reducing the bus duct size. The decision to reduce the bus duct size at the 6th floor is based on the principle of optimizing the electrical system design. The 1200 amps bus duct is only necessary to handle the higher load in the lower floors. Carrying a 1200 amps bus duct all the way to the top floor would be unnecessary and would result in increased cost, weight, and space requirements. By transitioning to a 600 amps bus duct at the 6th floor, the system can accommodate the reduced load in the upper floors while maintaining sufficient capacity. This optimizes the electrical system design and ensures efficient and safe power distribution throughout the building. Reducing the bus duct size also reduces the overall cost of the project. The 600 amps bus duct is less expensive than the 1200 amps bus duct. Reducing the bus duct size also reduces the installation cost. The 600 amps bus duct is lighter and easier to handle than the 1200 amps bus duct. Reducing the bus duct size also reduces the space requirements. The 600 amps bus duct is smaller and takes up less space than the 1200 amps bus duct. In addition to cost savings, reducing the bus duct size also improves the efficiency of the electrical system. The 600 amps bus duct has lower losses than the 1200 amps bus duct. This reduces the amount of energy wasted in the system. The smaller bus duct also reduces the amount of heat generated by the system. This improves the reliability and longevity of the system. Now let's focus on ampacity. Ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a bus duct is determined by the size and material of the conductors, the insulation type, and the ambient temperature. It is crucial to ensure that the 600 amps bus duct has adequate ampacity to handle the maximum load on the upper floors. This requires careful calculation of the load demand and selection of the appropriate bus duct size. The National Electrical Code, or NEC, provides guidelines for determining the ampacity of conductors. NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air based on ambient air temperatures of 30 degrees Celsius. Correction factors are applied for ambient temperatures other than 30 degrees Celsius. Adjustment factors are also applied when multiple conductors are installed in close proximity. It is essential to consult the NEC and manufacturer's specifications to determine the correct ampacity for the bus duct. Now let's address the connections. Proper bus duct connections are critical to ensure reliable and safe operation of the electrical system. The connections must be mechanically sound and electrically conductive. They must be able to withstand the stresses associated with thermal expansion and contraction. The connections must also be protected from corrosion. Bus duct connections are typically made using bolted joints. The bolts must be properly tightened to ensure a secure connection. The torque values for the bolts are specified by the manufacturer. A calibrated torque wrench should be used to tighten the bolts to the correct torque. After the bolts are tightened, they should be inspected to ensure that they are properly installed. A conductive joint compound should be applied to the contact surfaces to improve conductivity and prevent oxidation. The joint compound should be applied sparingly and evenly. The contact surfaces should be clean and free of debris. The connections should be inspected regularly to ensure that they are in good condition. Loose connections can cause overheating and arcing, which can lead to equipment failure and fire. Now let's talk about documentation and labeling. Clear and accurate documentation and labeling are essential for the safe and efficient operation of the electrical system. The documentation should include drawings, specifications, and maintenance manuals. The drawings should show the layout of the bus duct system, including the location of the transition. The specification should list the ampacity of the bus duct at each floor. The maintenance manuals should provide instructions for inspecting, testing, and maintaining the bus duct system. The labeling should clearly indicate the bus duct capacity at each floor. The label should be permanently affixed to the bus duct and should be easily visible. The label should also include the voltage and phase of the bus duct. The labeling should comply with all applicable codes and standards. In addition to the physical labeling, it is also important to maintain accurate records of the electrical system. These records should include information on the load demand, voltage drop, and maintenance history. The records should be stored in a safe and accessible location. Regular inspections and testing should be performed to ensure that the electrical system is operating properly. The results of the inspections and testing should be documented. Any problems that are identified should be promptly corrected. By following these guidelines, you can ensure that the bus duct system is operating safely and efficiently. It is important to consult with qualified electrical engineers and contractors to ensure that the design and installation meet all applicable codes and standards. Now, expanding on the documentation aspect further, comprehensive documentation is paramount for future maintenance, troubleshooting, and system upgrades. The documentation should include single-line diagrams illustrating the entire bus duct system, including the location of the main switchboard, the 1200 amps and 600 amps sections, the transition point, and all tap-off points. These diagrams should clearly show the ampacity of each section of the bus duct, as well as the voltage and phase configuration. Furthermore, the documentation should include detailed specifications for all components of the bus duct system, including the bus duct sections, transition piece, connectors, ports, and hardware. These specifications should include the manufacturer's name, model number, and relevant electrical and mechanical ratings. Installation records should also be maintained, including the date of installation, the names of the installers, and any deviations from the original design. These records should be updated whenever any changes are made to the system. Maintenance records are equally important. These records should document all inspections, tests, repairs, and replacements performed on the bus duct system. The records should include the date of the work, the names of the personnel who performed the work, and a description of the work performed. In addition to the written documentation, it is also helpful to have photographs of the bus duct system. These photographs can be used to document the condition of the system and to identify any potential problems. All documentation should be stored in a secure location and should be readily accessible to authorized personnel. Electronic copies of the documentation should also be maintained to ensure that the information is not lost in the event of a fire or other disaster. Now, regarding labeling requirements, clear and durable labeling is essential to prevent confusion and ensure the safety of personnel working on the electrical system. The label should be permanently affixed to the bus duct and should be easily visible from a distance. The label should clearly indicate the ampacity of the bus duct at each section. For example, a label at the main switchboard should read 1200 amps bus duct, while a label at the 6th floor transition point should read transition to 600 amps bus duct. The label should also include the voltage and phase configuration of the bus duct. For example, a label might read 480 volts 3-phase. In addition to the ampacity, voltage, and phase information, the label should also include a warning message, such as danger, high voltage, or do not touch. The label should comply with all applicable codes and standards, including the NEC inertia regulations. The label should be made of a durable material that can withstand the environmental conditions in which the bus duct is installed. The label should be resistant to moisture, chemicals, and ultraviolet light. The label should be applied using a permanent adhesive that will not peel or fade over time. In addition to the labeling on the bus duct itself, it is also important to label the electrical panels and equipment that are connected to the bus duct. These labels should indicate the source of power and the ampacity of the circuit. By providing clear and accurate labeling, you can help to prevent accidents and ensure the safe operation of the electrical system. Now, let's talk about load calculations. Accurate load calculations are essential to ensure that the 600 amps bus duct has adequate capacity to handle the maximum load in the upper floors. The load calculation should take into account all of the electrical equipment that is connected to the bus duct, including lighting, receptacles, HVAC equipment, and any other loads. The load calculation should be based on the actual connected load, not just the nameplate ratings of the equipment. The load calculation should also take into account any diversity factors that may be applicable. A diversity factor is a multiplier that is used to account for the fact that not all of the electrical equipment will be operating at the same time. The diversity factor will vary depending on the type of building and the type of load. For example, an office building may have a diversity factor of 0.75 for lighting, meaning that only 75% of the connected lighting load is expected to be operating at any given time. The load calculation should also take into account any future loads that may be added to the system. It is important to allow for future growth when sizing the bus duct. The load calculation should be performed by a qualified electrical engineer. The engineer should be familiar with the NEC and all applicable codes and standards. The load calculation should be documented and kept on file. The load calculation should be reviewed and updated whenever any changes are made to the electrical system. By performing accurate load calculations, you can ensure that the 600 amps bus duct has adequate capacity to handle the maximum load in the upper floors and that the electrical system is operating safely and efficiently. Now let's discuss the NEC requirements. The National Electrical Code, or NEC, contains numerous requirements that are relevant to the design and installation of bus duct systems. These requirements cover a wide range of topics including ampacity, overcurrent protection, grounding, and installation methods. It is essential to comply with all applicable NEC requirements to ensure the safety and reliability of the electrical system. Some of the key NEC requirements for bus duct systems include the following. NEC Section 368 covers busways. This section specifies the requirements for the installation and use of busways, including ampacity, overcurrent protection, support, and grounding. NEC Section 240 covers overcurrent protection. This section specifies the requirements for overcurrent protection devices such as circuit breakers and fuses. The overcurrent protection devices must be sized to protect the bus duct from overload and short circuits. NEC Section 250 covers grounding. This section specifies the requirements for grounding electrical systems. The bus duct must be properly grounded to provide a path for fault current to return to the source. NEC Section 310 covers conductors for general wiring. This section specifies the requirements for the ampacity of conductors. The conductors in the bus duct must be sized to carry the maximum load current without exceeding their temperature rating. In addition to these specific requirements, there are also numerous other NEC requirements that may be applicable to bus duct systems. It is important to consult the NEC and all applicable codes and standards to ensure that the design and installation meet all requirements. Now let's discuss the importance of using qualified personnel. The design, installation, and maintenance of bus duct systems should only be performed by qualified personnel. Qualified personnel are those who have the necessary training, experience, and knowledge to perform the work safely and competently. Qualified personnel should be familiar with the NEC and all applicable codes and standards. They should also be familiar with the manufacturer's recommendations for the bus duct system. Electrical engineers should be involved in the design of the bus duct system. Electrical engineers have the training and experience to perform load calculations, select the appropriate bus duct size, and ensure that the system meets all applicable codes and standards. Licensed electricians should be involved in the installation of the bus duct system. Licensed electricians have the training and experience to install the bus duct safely and correctly. They should also be familiar with the manufacturer's recommendations for the installation. Qualified technicians should be involved in the maintenance of the bus duct system. Qualified technicians have the training and experience to inspect, test, and repair the bus duct system. They should also be familiar with the manufacturer's recommendations for the maintenance. By using qualified personnel, you can help to ensure that the bus duct system is designed, installed, and maintained safely and reliably.